Hi, my name is Zhishen Yang. This lecture is building and deploying pins-based solvers. Me and my coworker Aditya Bulu are from Iowa State University. We two will cover this lecture together. This is today's outline. First is about recap on pins and implementing pins. Third, we will have a hands-on section. Finally, Aditya Bulu will help us go through deploying pins and the conclusion parts. So we will start this lecture from summary on pins. As I mentioned from that section, the inputs of the pins are the space domain and the time domains. As we can see in the figure, the X and T from the left-hand side is our input. The loss function is contained two parts. The first part is from residual. The second part comes from our condition equations. And the physical property is learned by backpropagation while the neural network is training. So how to implement pins? To implement the code to write our own physical info neural network, we need to predefine the following information. First is our computational domain. Second is our PDE equation. Third is our conditional equation. Fourth is our training data and our architecture of the neural network, and also the optimizer and initializer for the network. So as we can see in the figure, to define the training data, we first need to have our geometry definition of geometry and our PD equation, boundary initial conditions, and our training data. And then we'll feed those information into the model. Within the model part, we also need to tell it what does our neural network looks like. Then we compile the model, train the model, and get the result from the model. So to start implement our code, we need to we can start from a package called DeepXD. This package is divided by Lulu, and it's based on a very popular and wide use package, machine learning package called Tensorflow, which is written in Python. And here are its dependency. First, you need PyTorch and TensorFlow. To install DeepXD is quite simple. You can install it using the pipe. Just pipe install DeepXD, or it also can be installed using Conda. And also you can use GitHub to install it. After we have the package, we can learn the basic workflow of how does it work in the package or in the code. So first step is that specify the computational domain using geometry module. Second is define our PDE in the grammar of TensorFlow as it is based on TensorFlow. And third is that we need to specify the boundary and initial conditions. Then we combine the geometry, PDE, and those boundary initial condition together into data.pde or data.time PDE, which I will go through the details later on. The fifth point is I map the module, map the neural network, and also the data that I just defined. And I combine it and compile it train it, and get a prediction from the model. So this is just a basic step-by-step workflow. So to make it work, we are going to learn some functions and methods, some module in DeepXD DeepXD package. And I will went through these 9 stuff one by one. And for the following explanation, let's just use a heat 1D equation as an example for easier explanation. So the heat 1D equation that I'm going to use, the PD equation, is partial U over partial T equals to alpha partial square U and partial X squared, which my X, I would like to set it between -1 and 1. And I would like to have the T between 0 and 1. My initial condition and boundary condition, I just set it to be the same as sine pi x expansional minus T. So the first step is define the computational domain. This function is quite easy to use. As we can see, geo equals to DDE dot geometry the interval -1 to 1. So this is the simplest way to define our geometry within 1D. We can use the interval function, and you just need to input your minima of the geometry, your x-axis, and your maxima. The time domain, we can use dd.geometry.time domain 0, 1, because I would like to have results from t equals to 1 to t. So t equals to 0 to t equals to 1. Geo time is just a simple function to combine my geometry information and my time domain information together. So after that, when I train my model, my training data and testing data will be randomly sampled from the geo time domain. After we define the computational domain, we can define our PDE. We can use any method to define it. Just make it TensorFlow readable, or we can also use some function from the DeepXD package. So here what I use is the Jacobian and Hessian function. So I just define the PDE and return dyT. So the y here is the output of the model. The lower x here is the input of the model. So lower x here actually has two, it's a 2D array, kind of 2D array. The first is the first dimension is my x, the second is my time. And absolutely in the network, it will be represented as tensor, but we can have a simple understand that it is a 2-dimensional tensor. First is my geometry, and the second is my time. So the lower x actually contain these two. The y is my output, which is the temperature of my heat equation. And then we can define our condition equation. So just define a function, return whatever you want to return, just using dd dot calculate BC, and put the geo time we just define as one of the input. The function we just define is another input, and set the boundary condition to be unbounded. Similar things happens in my initial condition. I just use dd.ic, stands for initial condition, and input my geo time, my function, and set sets it to be on initial. As for the training data, yeah, the training data, I also input my dwell time, my PD, and the boundary condition and initial condition I just defined. They are all my inputs, and then NUM dash domain equals to 4,000 means that while I train the model, I would like to random sample 4,000 points in my dwell time area, in my dwell time domain. And when I train my model, I would love to like sample another 2,000 points from my boundary and 1,000 points from my initial. So this total 7,000 points are my training data. The non-test equal to 1,000 is for us to monitor the training process. So I will have 1,000 points from random sample from the dwell time to work as my validation data set while I train the model. After I have all my data, I designed our architecture of the neural network. As we can see here, layer size equals to 2 plus 32 times 3 plus 1. What does it mean? The first two is my input size, which is 2, my x and t. The 32 times 3 stands for 3 dense layers. Each layer I has 32 nodes. So that is 32 times 3. And the final one is my output of my neural network, which is my heat. So it's only one dimension, so it's 1. So that's how to define your architecture of the neural network. You can absolutely change the number of layers you want to have and the number of nodes you want in each layer. The activation function here, I just use 10 function, which can be see here is range from -1 to 1. I choose this because every point in every point in the 10 function is differentiable, and 10 function is also a well-used activation function in deep learning. After that, I combined those information in my in my neural network. And I also define my optimizer and initializer. I define my initializer as glow-rent uniform. Glow-rent uniform is a uniform distribution for my weights and for my bias for everything, every parameters in the net. It's just a uniform distribution within a limit. And the upper bound and the lower bound of the limit is related to my network architecture. The optimizer I choose here is also very well-used optimizer called Adam. After I have all of the information, I compile the model. Just use maps FNN to just map all the information together into my network and compile the model. Compile the model, the network with my training optimizer, my learning rate. And the metric here, L2 relative error, is another method for us to monitor the training process. After I have all of these, we can train the model. So we can plot the loss history later on. If we just set loss history and train state equals to the model.train, then all the loss function from the training data and testing data. Also, the metric I just mentioned here will be recorded in the loss history. And here I set my training app cost to be 10,000. After I train the model, we can get the training result from the neural network as well. So for here, I just defined a grilled point with x within the range of -1 and 1, and t with the range between 0 and 1. I just made the grill point to be my input to the model. As we can see here, predict solution equals to model.predict test domain. Test domain is just the grill point I just made up. And then we can have our predict solution. And also we can use the same function to get our residual. Just change operation equals to PDE, then it will output the residual. So this result is the same result as I showed in lecture 3. We can also have a quick look of some other equation that that we might be interested into too. So here what I show is the burger equation, and also is in one dimension. The burger equation looks a little bit complicated than the heat 1D equation. So it's just v partial square u over partial x squared equals to partial u partial t plus u times partial u over partial x. So we can see in the PDE defined part, we just use this part minus left-hand side. So as we can see here, it's partial u over partial t plus the u, which is y in my code. So the y is the same, it's just the output of my neural network, which is the u in the equation. So it's partial u partial t plus u times partial u over partial x equals to the left-hand side of the equation. So here I just define my PDE and my x. For this time, I want to define it anywhere from -5 to 5. My time domain, I would like to see it from 0 to 9.99. So it's just a change of some numbers in the geometry.interval and geometry.time domain. And I just do the same thing. I combine my geometry and time together to form my geotime. And I like to set my boundary condition to 0. And also I have some initial condition, which is minus sine pi x. And also I combine all information above to define my data. In the data, I have geotype, my PDE, my boundary condition, initial condition, how many training data points in my geotype, how many training data points in my boundary, how many in my initial. Also, I have my network. Here I have I still have 2 input, which is my x and my t. In this time, I have 3 hidden layers. Each layers I have 20 nodes. So we have multiple expression for how many nodes and how many hidden layer we want to have. Here I just use 20 plus 20 plus 20. Previously I just used 32 times 3. And all of these are readable for the code. And my output is 1 dimensional, so it's +1. And here I still choose my activation function to be 10, initial to be initializer be global normal. Model it, compile it, train it. And here are my results of that. So as we can see, the residual is quite low. It's almost 0 everywhere. And the left-hand side is my predict solution from the trained neural network. As we can see here are a little bit weird, but it's not weird actually, because I set my initial condition to be a sign function. That's why we can see 1 to minus 1, 1 to minus 1. And we can also have 2D equation. So here, I not only define my PD equation, I also change the network architecture to be 3 plus 20 plus 20 plus 20 plus 1. So why is 3? Because here I have my X, Y, and time. So for here, my input dimension is 3. And here I can have a short talk about what is RAR. So here I just detect after I train the model for several app codes, I just like compute, or I pick those points which has the most residual, means that they have the most error, the most predict error, the most lows from the PD equation. I choose those most wrong training data points and to train it again. So this is for us to increase the accuracy of the model, because I just calculate who is the worst point and add those points to my training set. And here are my results. And because it's the 2D X domain, Y domain, and time domain, I just make it to be a video. So the result is changing by time. As we can see, the residual will be within 1%. Means that we are about 99% accurate. And it's just a quick comparison of when t equals to 10 seconds, what's the solution looks like. So the left-hand side from our ping model, the right-hand side is from FDN simulation result. Okay, so after we saw those example, next we are going to like show the code and run the code from a 1D heat equation and change it to 2D PD equation. Okay, so here is the heat 1D equation and that I just show, and we also saw the result of it. So let's say now I want not heat 1D but heat 2D equations. How to like change it from 1D to 2D is our topic today. So like, let's say for the PDE part, now we will have not only for X, but also for Y. So we want like partial U, partial Y, partial U, partial X, partial U, partial T. Okay, So let us use some grammar from TensorFlow. So let's say we have dy over x equals to, we can use the TensorFlow that tf.gradients. From here, tf.gradients and gradients to our output and our x. So this basically means that we want partial y over the gradient of u, and which is partial y over partial x. And okay, then we can follow up dy dx, and we want especially so for this line, it will give us all the partial of the output, which means that it gives us the partial y, partial x domain, partial y domain, partial y, partial t domain all the time. But in our equation, we only want, like, we sometimes want partial y over partial x, partial y over partial time, right? So we need to like specify which one do I want. So let me just do a really quick from here. Okay, just change the symbol. Oh, or just make it easier. Just use u. Partial u over partial x, partial u, partial y. Okay, equals to then by doing so, I will, so for the dux is for the du over partial u, partial x is my first array of the gradients. So from doing so, I basically say that, oh, when I call du lower x, then I will only get partial u over partial x domain. When I call du y, then I will only get partial u over y domain. And this is more like what we want. And then we can have these two lines. Basically, I just do the gradient on the du x a second time, which means that, which basically partial, so it's partial u, partial x, and I do the gradient again. So I will get partial 2 times from that. Okay. Let me just change everything to be, okay. Just change everything to be upper class. Then by doing so, and I specify in the gradients, I only want the first one, which is the x domain. For partial u square, partial square y, I specify that I only want the second term from the gradient, because when I call tf.gradients, it will give me all the partial term at once. So I just specify that which one I would like to have. After that, I can use those symbols to say what exactly I want to have. So here I will have my my PD equation is partial u over partial t equals to 0.5 times partial u squared partial x squared plus partial u squared and partial y squared. So it's second partial, second derivative. And for my function, so now my first dimension of the input is x, my second is y, my third is t. Okay, and I could also change my initial condition and boundary condition to use x, y, and t also. So for now, I only use the first input, which is x, and the second input here will be my y. So I want to change it to use like x, y, and t. So again, because the lower x actually stands for the input of my neural network. Well, the inputs actually contain 3 dimensional. One is my x domain, second is my y domain, third is my time domain. So I think the lower x is a little bit confusing, but the x here stands for the input, which is 3-dimensional. But one is x domain, y domain, and t domain. Okay, so for define the geometry, now it's not only the interval, because interval is just for a line, like for if my geometry is only 1 domain. But now I want to change it to 2 dimension. So instead of interval, what I can use is 2D rectangle. So 2D rectangle here, -1, -1, 1, 1. So what does that mean? It means for x, I would like a rectangle. So it's just the left bottom edges, the left bottom point of the rectangle, and the right up point of the rectangle. So it's -1, -1, 1, 1, which means for x, I would like to range from -1 to 1. For y domain, I would like to range from -1 to 1. Okay, and for the time, I don't need to change anything because it's, yeah, we can keep it the same, just 0 to 1. For the geo time, it's the same as well. It's just combine my geometry and my time domain together. For boundary condition, initial condition, we are all good. It's not, yeah, it's just geo time function on boundary. Okay, for the data, we can actually keep it the same. So for here, I have 8,000 training points that will be randomly sampled from my geo time, and 2,000 points from boundary, and 3,000 points from initial condition. And I have another 1,000 points for my validation loss. My layer size. Now my input is not 2D anymore. I have 3D input, which is x domain, y domain, and time domain. So these definitely need to change to 3. Okay, because now we are doing like a little bit more complicated because we are from 2D input to 3D input. So we can just change it, maybe a larger. Actually, we can do it like 4 layers, a little bit deeper. Activation function, initializer, we don't need to worry about that. Network just maps the layer size and these two together. Okay, we are all good. And compile the model. to tell it what's the optimizer and the learning rate. Okay, we are good now. Train the model and plot the model. Okay, for the mega testing domain, I also need to make it to 3-dimension. So it's just a simple change of that. And then we are all good. We can plot it. So here is my today's portion. Thank you.